So welcome back, and we're looking today at the iron-carbon phase diagram. And we have a couple of objectives today. Big dose of vocabulary that you need to learn, and then some key concepts, microstructural concepts, that will be applied in the TTT diagram. So here's iron-carbon diagram is presented in your textbook, and you notice some key features. Here's your room temperature. It's a two-phase system, and alpha, or ferrite, is a body-centered cubic iron. And you have a couple of key points. This point, at the 4.2 weight% carbon, and 1153 degrees C, you have three phases in equilibrium, liquid and two different solid phases. So that is a U, the phase is above the line, a single phase region. And because it involves a liquid, it's icky, so this is eutectic. And this is really important. This melting temperature suppression with carbon addition is what gives us cast irons, and they're commonly used. So we need iron, but you'd like to cast them, and you'd like to melt them at as low a temperature as possible. And you see that adding carbon suppresses the liquidus line, and so they melt at a significantly lower temperature. The other point that's interesting, and this is the key point for defining the whole family of iron-carbon alloys that we call steel, is this transformation from austenite to ferrite, and we usually say cementite, a two-phase solid region here. So single phase, this is FCC, or face-centered cubic iron, has a very high solubility of carbon. Notice you can dissolve up to 2.1% by weight carbon if you're at the right temperature in austenite, so it has high solubility. Ferrite, by contrast, here on the left edge, the alpha region, has very low solubility for carbon. It's about 0.02 weight% max. And so dramatically different solubilities there. And then the key to steel is going to be the ability to heat up and make a single phase FCC system, and then to cool that system down and have those solid grains of austenite separate into ferrite and cementite. So this eutectoid point is a very important point for us. So as we think about these terms we're just introducing, the ferrite is the name we give to BCC iron. Has moderate or to small amount of carbon. It's fairly moderately hard anyway. Austenite is FCC iron. It has a lot of carbon, and because it's FCC, it's very ductile. It's not particularly hard. And then cementite is an intermediate compound. Fe3C is actually the formula, so 3 irons and 1 carbon, and it's going to play an important role in the microstructure that develops. Maybe use a little better diagram because it uses a number of labels that we need to learn. So again, here's your austenite boundary. Fe3C is an intermediate compound. It's 6.7 weight% carbon. So this is a vertical line. Remember, intermediate compounds are phase regions that have no width. And we break steels into two major categories. Those that have more carbon than the eutectoid composition, which is about 0.77%. So hypereutectoids are 0.78 and above. And that is, they have more carbon than the eutectoid composition. And hypoeutectoid steels have less carbon than the eutectoid composition. And then steels are broken down. Notice the bottom here, low carbon, medium carbon, high carbon. And high carbon still ends. We have to have a full austenite region that then will separate into two-phase regions. Possible for the alloy for it to be a steel. When we get beyond that, where we never have a full single-phase solid, we're now operating in the cast iron region, which is what's going on here. And these are cast irons, and anything above about 2% carbon. Okay, so again, ferrite is alpha. Austenite is the gamma, or FCC iron, and cementite is what we call this intermediate compound, Fe3C. Now, let's look at a sample. We'll start at this composition. It's like 0.55% carbon. Actually, I guess it says 0.52. And we're going to start out at point A. So it's hot enough that the sample of material exists as a pure austenite state. The austenite has the solubility to dissolve all that carbon, and so at point A we have a single phase gamma iron. As you cool that sample, when you get to the ferrite austenite boundary here, at point B, we're going to begin to make a new phase. So we keep the austenite, but some of the austenite will transform to ferrite. And so this two-phase region now that we've entered, we're beginning to form ferrite. And this ferrite is forming before the eutectoid temperature. This temperature B is above the eutectoid, which is this line. And so we call the ferrite that's forming now pro-eutectoid ferrite, or ferrite before the eutectoid. Now, as we cool through the ferrite austenite region to point C, we are making more and more ferrite. And if you do your reverse lever law, the proportion to ferrite is the opposite distance, so it's from C to 0.77. And you see that distance is getting larger. As we add B, there is nothing beyond B. And as we move down, the distance is getting greater and greater. So we're making more and more ferrite. And at this point, the total length of this line is 0.77 minus 0.022, so it's about 0.75. If this point is at 0.52 minus 0.22, then this length is 0.5 and this length is 0.25. So the fraction that is converted to ferrite is the opposite, 0.25, divided by the total, 0.75, or we've made about 1/3 of the material at point C that's turned into ferrite. Now, if we could look at this in a microscope, and it's difficult to at 740 degrees, but if we could, what we would see is that at point C, we're here with image B. We have formed ferrite regions around the grain boundaries of the austenite. The austenite, again, is FCC iron with a lot of carbon dissolved in it. And ferrite is fairly poor in carbon, so carbon has had to diffuse out of the ferrite and collect in the austenite. The ferrite can't hold it. So the amount of carbon in the austenite is increasing. And in fact, if we go back, if you do your tie line at point B, the composition of the austenite is 0.52. As you go down, the carbon content of the austenite is moving to the right. And so at point C, the austenite has 0.77 weight percent carbon in it. So you see the amount of carbon in the austenite is increasing. And obviously the ferrite is also picking up more and more carbon as we move down. This boundary is moving to the right. So we start at almost 0 at point B. There's very little carbon over here. When we do the tie line, right, composition is almost no carbon. But as we cool down, we see more and more carbon in the ferrite phase until we get to the eutectoid temperature. So your prior phase diagram information, tie lines, and reverse lever law should allow you to identify that we have about 1/3 ferrite at this point. The ferrite is poor in carbon from the tie line. The austenite, which is 2/3 of this surface, is going to be richer in carbon than the overall material. And this is running about 0.77% carbon at point C on the phase diagram. Now, when we cross the eutectoid, it is now too cold for any of the austenite to remain. And so all of the remaining austenite will convert to a combination of ferrite and cementite. And now this diagram is labeled ferrite and pearlite because the ferrite and cementite that forms from the austenite is going to arrange itself in a lamellar structure. And that pearlite consists of alternating layers of ferrite and cementite. The intermediate compound, cementite, the black bands here, and the white areas are the ferrite regions. The cementite is rich in carbon, 6.7 weight percent carbon, because it's an intermediate compound, and the ferrite is very poor in carbon. So a lot of diffusion has had to happen for this to happen, for us to get this microstructure, because the carbon has to leave the ferrite and collect in these cementite regions. Now, pearlite is the structure that forms when we cool very, very slowly through a eutectoid temperature. And it's common, this name is used not just for iron carbon, but you'll hear pearlite described in other systems as the slow cooled or the equilibrium structure in a eutectoid system. Now, if we're at the eutectoid composition exactly, when we cool from austenite, so let's say we start at point A, we have austenite grain boundaries. We hit the eutectoid, no proeutectoid phase is formed. When we cross this temperature, all of the austenite converts to pearlite, alternating layers of ferrite and cementite. And there is no ferrite that formed along the grain boundaries to start with. Okay? So no proeutectoid phase at the eutectoid. We just go straight from austenite to alternating layers of ferrite and cementite down in this two-phase region. Finally, if we're talking about a hypereutectoid steel, you should be able to look ahead and figure out what's going on here. We have a composition to the right of the eutectoid. As we're cooling down, we're going to begin to make cementite in the proeutectoid or above the eutectoid temperature. Where is that cementite going to form? Probably along the grain boundaries. So I should see grains along the grain boundaries that represent the formation of this cementite. And then when we cross the eutectoid, in the middle of the grains of austenite will be pearlite again. And in fact, that's eutectoid steel. You see no grains at the boundaries. And this is hypereutectoid steel. These are grains along the boundaries that are proeutectoid cementite, formed before the eutectoid. And then this is pearlite again. Looks just the same as the pearlite in the other two steels. But we're alternating layers of ferrite and cementite, and this formed below the eutectoid temperature. So we care about whether steel is hypo or hyper because knowing that tells us what this proeutectoid phase is that's forming on the grain boundaries. This is the proeutectoid phase, always forms on the grain boundaries of the austenite. And the only reason I know this is cementite in this picture, since it's white, just like in the hypereutectoid steel, is I know this is hyper, so that must be cementite forming. Okay. So why do we add carbon? We've already hinted at this. We talked about this with alloying and so on earlier this semester. Adding carbon increases the yield strength, increases the Brinell hardness, increases the tensile strength. One of the things that it doesn't do for us is improve toughness, and we see the IZ impact energy drops, reduction in area drops, elongation drops. And that's by altering the carbon content. Now what's exciting about steels is we can take a particular carbon content. We can also alter the properties by selective and careful heat treatment, and that's the next thing that we want to talk about in our next session.